So we're going to talk about chapter 6 of the Statistics and Mechanics book 1, which is called Probability Distributions. So this is going to be a really new concept, so we're going to have to really talk a little bit about what a probability distribution is. But before we talk about a probability distribution, it's probably worth talking about the umbrella term for this whole topic, which is also a new term for you. So let's write that down. That's called a discrete, spelt R-E-T-E at the end, as opposed to the discrete with two E's, which means something completely different. Random variable. And what we should do is we should discuss each of those words, because that whole three-word discrete random variable probably seems a bit daunting to you at this stage. So let's explain exactly what each of those words mean. And I'm actually going to work from right to left. So let's get another colour. Let's go red. So let's first of all talk about a variable, which you're probably familiar with. Okay, a variable, as you have seen in other places in maths, is usually a letter that takes a certain value, x, y, right? We deal with lots of variables in maths. So a variable in this context, okay, which is going to be denoted by a capital letter, okay, capital letter. So I'll say, for example, x is the most popular one, okay, or y, for example. That variable is some sort of experiment that will generate a numerical value. If you do an experiment, you don't always get outcomes that are numerical. For example, when I toss a coin, for example, I get a head or a tail. Now, a head is not a number. The outcomes of that experiment are not numerical. We're going to see later we can actually play around with exactly how we define the experiment to ensure that tossing a coin can be considered a discrete random variable in various circumstances. But on a most basic level, a variable, you should write this down, is an experiment with numerical outcomes. So the variable is the thing, the physical activity that you are doing that will generate numerical outcomes. So a variable in this instance could be throwing a dice. When I throw a dice, what happens? I could get a 1, a 2, a 3, a 4, a 5 and a 6. That's the only things that can happen. So I'm getting numbers from that activity. It has to be something that will generate numbers. Now, random, we have to be very precise exactly how we're going to define random. We're not talking about random as, oh, that's such a random thing to do, or something like that. Okay? The important aspect of randomness here is that there is no bias. In other words, there is no predetermined conditions that the probability of getting a 2 on a dice has to be a certain probability. Now we know that on a fair dice the probability of getting a 2 is 1/6, because that's a fair dice, that's what happens, it's completely fair. But in other experiments, okay, you can't fix certain outcomes. You won't mess around with it. It's got to be completely random. You only will know that the probability of certain outcomes after you've actually done the experiment. There's no bias there. Now, discrete is a word we've come across before. Okay, discrete means that the outcomes are countable. I could physically write down all the outcomes if I wanted to. So a discrete random variable is a numerical experiment, an experiment that gives numerical outcomes, which there are no bias on any of those particular outcomes, but the outcomes form a finite list. I could write down all the outcomes. 1, 2, 3, 4, 5, 6. Now, it's probably worth saying at this point, well, can we always do that? Well, the answer is no. Okay, we can't always write down all the outcomes. For example, I'll give you an example of the opposite of a discrete random variable. You may have come across before the opposite of discrete, and the opposite of discrete is continuous. And there is such thing called a continuous random variable, but we deal with that more next year, in year 13. But a continuous random variable, for example, would be the weight of a baby. When babies are born, they have a weight. It's a number. But I cannot write down in a list all the possible weights of babies when they're born. Okay? That's not a finite list. How, I could always be more accurate. I could do it to 2 decimal places, to 3 decimal places. And also, although there are a certain range of values that the weight of a baby might be, okay, it might be between X and Y, would it, okay? Right? It could take any value in between. The same with height, the same with IQ, things like that. So things that are continuous is things like IQ, height, weight, even age. Right? We commonly talk about our ages as 5 years old, 6 years old, 7 years old, but I could in theory say that I'm 17.345 years old. Okay? We don't do that, but we could do that. Okay, so things like time, height, weight, they are continuous. But we are concerned with a discrete random variable. Okay, things that form a finite list. Now, if you haven't done so already, I recommend jotting that down. So we're considering a discrete random variable. All we've discussed so far is a description of the actual activity we're going to do. Okay, all we've said is we're dealing with an experiment with numerical outcomes, and we've added on that, okay, it's not supposed to be biased, and the outcomes have to be countable. So that leads on to the name of this chapter, which is a probability distribution. Very, very important. Let's discuss a probability distribution. There's a lot of new definitions here, so you're just going to have to write them down and study them to consolidate them. A probability distribution. Right, a probability distribution, which is sort of a funky name, but it's actually quite simple. It's also known, I'll just put this in brackets, but make a note of it, it's also known as a probability mass function. The same name to describe exactly the same thing, but in an exam question they may refer to it as a probability mass function. So anyway, a probability distribution or a probability mass function, what is that? It's quite simple. It's effectively a table that summarizes your experiment. So what is a probability distribution? It is simply a list of outcomes. Remember we said that the outcomes are numbers. Okay, so in my discrete random variable, in my experiment, I've got a list of outcomes, okay, the list of the outcomes, and also a list of the probabilities for each outcome. So it tells me everything that I want to know. It tells me what can happen, what are the outcomes of my experiment, of my discrete random variable, and what are the probabilities of each of those outcomes. And you will be asked to write down a probability distribution, and that is basically to write down a table of the outcomes and a table of the associated probabilities. And I want to show you exactly how we use that, because there's a bit of notation that is quite important that we understand. So let's do that now. Okay, so in an experiment, right, we want to be very clear as what the definition of the discrete random variable is. So I'm going to call my discrete random variable capital X. And my discrete random variable, remember, which is an experiment that generates numerical outcomes, is going to be, you have to be very precise, it's going to be to throw a dice, okay, throw a die, and record the uppermost face. Now, in the exam question, you'll read potentially a little story of what's going on, and you'll have to identify what the discrete random variable is. You're not supposed to make up your own example, okay? But I'm going to consider the situation, I'm throwing a die and recording the uppermost face. That's capital X. Now, the probability distribution, which I'll call the PD, the probability distribution, and they'll probably ask for it in an exam question, and even if they don't, for whatever reason, you will basically need to write it down, because everything in the probability distribution, which is a table, is going to enable you to answer whatever else they ask. So what do we need for a probability distribution? We need the outcomes. Now, the outcomes of a discrete random variable is denoted by the lowercase letter of whatever the discrete random variable is. I've used capital X for the experiment, so lowercase x represents all the outcomes. Now, sometimes the exam question will tell you in black and white what the outcomes are. Here it doesn't. Why? Because my experiment is to throw a dice. I know what happens when I throw a die. There are 6 possible outcomes. 1, 2, 3, 4, 5, 6. There might be a scenario where you're using a spinner, and they'll have to tell you the spinner's got 4 sections. How am I supposed to know? I'm not an expert in spinners. So in this case here we've got 1, 2, 3, 4, 5, 6. Now when it comes to a dice, they're going to have to tell you whether it's biased or not. Okay, so I've written throw a die. Let's just assume it's an unbiased die. Okay, so it's a regular dice, which means that the probabilities of each of these outcomes must be 1/6, 1/6, 1/6, all the way through. Now, what's the label for the probability for this? You notice I sort of just skipped that off. There was a reason for that. So let's just draw this here. Now, the way we label probability is as follows. These are the probabilities. We say P, a big P, which we've seen before. Okay, the probability P, and we say as follows: capital X equals the lowercase x, which looks a bit weird, and a lot of people just sort of float between capital X and small x without sort of worrying about what the difference is, and that's an issue. Okay, you have to worry about what the difference is. What does this mean? This means, let's translate it. Okay, it means what's the probability that capital X, what's capital X? It's throwing a dice. So this means what's the probability that when I throw a dice, I get small x, the particular outcome. Remember, small x represents, that's just a generic kind of family name for the outcome. It's like you've got a family, right? You've got a family name, Smith. Okay, X represents Smith. Okay, and these are the particular types of Smith. Okay, so that's just the generic letter, small case, to represent outcomes. That's the particular X. Right. So this means what's the probability of that you throw a dice and you get X? Well, in this column, the X is 1. So that really means probability X is equal to 1. So it's telling me that the probability that when I throw a dice and get a 1, I get a 6th. Over here, fill in small x with the relevant small x, probability X equals 4. That means that's the probability that my experiment will generate 4. That my throwing a dice activity will land on 4. And we have this table here. Notice if your capital letter is X, then it's this. If your capital letter is another letter, so let's say T, okay, then it would be this. So that would be that the probability of whatever I'm doing is equal to the specific outcome in the table. That is just the label for that. Now there is a special name for when a probability distribution has the same probability for every single outcome. Okay, and this is a term they can use in an exam, and it's a term you must write down. It is called a discrete uniform distribution. A discrete uniform distribution. So if you are told in the exam that you're dealing with a discrete uniform distribution, it means all the probabilities are the same. So if you know how many outcomes there are, it must be 1 over the total amount of outcomes. Because here there's 6 outcomes, so each of the probabilities is 1 over 6. If there are 10 days, for example, you're doing an experiment for 10 days and it's each equally weighted, then the probability will be 1 out of 10. That's a discrete uniform distribution, a very important term that is overlooked, but it has come up in quite a few exam questions. So there we have it. So that's what we need when we need a probability distribution. Now notice when you're throwing a die, okay, it's quite easy. You know what happens when you throw a die. I can tell you straight away without even thinking that the probability of getting 1, 2, 3, 4, 5, 6 is a 6th. There are certain discrete random variables where you're going to have to do a little bit of maths, a little bit of calculations, hard work, to work out what the probability would be for each outcome. You might have to do a little tree diagram, you might have to do some sort of GCSE probabilities, okay? Probably not as far as dealing with a Venn diagram, but it's not out of the question. So let me give you an example where I want you to create a probability distribution, but you're going to have to do quite a bit of calculation to create a probability distribution. Now if you remember, I said that tossing a coin is not a discrete random variable by itself. And that is because when I toss a coin, what do I get? I get a head and a tail. Heads and tails are not numbers. But I'm going to actually reframe my discrete random variable where we're going to be tossing a coin, but the actual thing that I'm looking for will be a number. Okay, so I'm going to write down a discrete random variable. I want you to try and calculate the probability distribution for me. Okay, so we've got this scenario here. 3 fair coins are being tossed. X, capital letter X, represents the number of heads obtained in the 3 tosses. Joe, so do you see what I mean? I can't use a discrete random variable for tossing a coin once, because all I get is a head or a tail. But I can toss a coin 3 times, and I'm not interested in the heads, tails, tails as an outcome. I'm interested in just counting the number of heads. Now, when you count how many heads you get, that's a number. So that's a discrete random variable. That's fine. And it wants you to find a probability distribution. So I want you to think about this very carefully. When you are asked to find a probability distribution, you are asked 2 things. You are asked to find what the possible outcomes are. So you need to decide very carefully what all the possible outcomes are. And then you have to work out all the probabilities using the right notation that we just introduced. So can you pause the video? I suggest writing this down. Have a go. It will take a little bit of time because you're going to have to do some calculations and thinking. So pause the video, and when you're ready, press play, and we'll go through it. Okay, so let's take a look. Now, what we're doing, we are throwing a coin 3 times, and we're counting the number of heads. So you have to ask yourself, what are the possible outcomes? How many heads could I get when I toss a coin 3 times? So the outcome that's most neglected is 0. If I toss a coin 3 times, I could be unlucky and I could get tail, tail, tail. I could have no heads at all. So you must make sure that you include the possible outcome of 0. And then you could have 1 head, potentially. You could have 2 heads. And you can be lucky and get heads all 3 goes. And then we have the probability label, where the probability that my experiment, which is tossing 3 coins, equals each of the individual outcomes. Now the easiest ones to do is this one and this one. Because if I have to work out the probability of 0, which means the probability that when I toss a coin 3 times that I get 0 heads, tells me, okay, 0 heads. You have to ask yourself, well, what does that mean? What needs to happen? If I want 0 heads, it means, I'm still tossing it 3 times, it means I must not get a head every single time, which means that I'm getting a tail, and a tail. Now the probability of a tail, 1 individual tail, is a half. So I need a tail on the first go, a tail on the second go, and a tail on the third go. And we know from the axioms of probability that if you want 3 probabilities all to hold simultaneously, we multiply them. Which means the probability of getting tails all 3 goes is 1/8. And it's exactly the same for this, because if I want x is equal to 3, it's a different row, sorry, it's a different column of the table, but effectively it's the same thing. Because if I want heads in every single go, I want head, 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 but the probability of getting a head is the same as the probability of getting a tail. Now, if this was a biased coin, they wouldn't be the same. Because let's say the probability of getting a head was 3/4, so this would be 3/4 times 3/4 times 3/4, and this would be 1/4 times 1/4 times 1/4. But the principle is the same. The tricky bit is this. Why? Well, let's have a look. If I want to get 1 head in the 3 trials, it means I want to get a head followed by not getting any more heads. I'm not allowed. I'm only allowed to get 1 head. Now the probability of a head is 1/2. The probability of a tail is also 1/2. And I want these all to hold. So is the probability of getting 1/8? The answer is no. Because the probability of getting 1 head, it's not specified where that head occurs. That's just the overall probability of getting 1 head. Who says I can't? Who says I have to get the head on the first go? I'm tossing a coin 3 times, that's it. There's no further conditions. The discrete random variable doesn't say we keep on tossing, okay, until I get a head, and when I've got a head I stop. No. It's tossing a coin 3 times, very vague. I just have to get one head. So that's one way of doing it, but look, you have to work out all the combinations. Maybe I'll get the head on the second go, which means I have to have tail on the first and the third. Each of these, again, is always a half. You have to be careful. It's not a biased coin. Other examples where there's some bias in the actual coin would mean you'd have a quarter and 3/4. Here, there's just halves everywhere. So that's another eighth. But there's another way of doing it. You can have the head on the third go, and you just have to check that you've encapsulated all outcomes. So there's 3 lots of 1/8. There's 1/8 here for this outcome, 1/8 here, 1/8 there. We know the OR rule in probability. If this can occur this way, or this way, or this way, you add up. So it's 1/8, 1/8, 1/8, which makes 3/8. Similarly, there's 3 different ways that you can get 2 heads. You could have heads, heads, tails. Right up here. Heads, heads, tails. You can have the heads at the end, or you could have one at the beginning, one at the end. They're all worth an eighth. 3 of them makes 3/8. Now, one example like this, where you have to... So examples like this, where you have to really think carefully of all the different outcomes, it's very easy to forget and miss an outcome. And you'll know if you have. Why? Because look what I've got. This row is the probability of my outcomes. And my outcomes have to all have a probability of 1 when you add them all together. If you pull all the outcomes together, the total probability has to be 1. That's what we call the sample space. Okay? So all the probabilities of everything you do in an experiment has to add up to 1. That's the rules of probability. So look, 1/8, 3/8, 3/8, 1/8, you can see sums up to 1. You write it like this. The sum of the probabilities, all of the probabilities, equals to 1. So let's say this was like 2/8, so I was a bit short. Almost always you're short because you've missed an outcome. Sometimes we double up. Sometimes we have too many outcomes. If I get the sum bigger than 1, that's also an issue. Right? How can the sample space have a 110% probability of occurring? It doesn't make any sense. Okay? So that's an example of a probability distribution for a more contextual example. Another slightly different presentation of the way an exam question can occur is where they don't really necessarily tell you what the discrete random variable is. And you might say at this point, well, if they don't tell me what the experiment is, they don't tell me the discrete random variable, then how am I supposed to know what the outcomes are or what the probabilities are? So if that occurs, your luck is in. This is far easier than the wording example we just did just now. So what they would do is they would summarize the information you need for your probability distribution in the following way. So what they might do is they might say something like this. X is equal to 1, 2, 3, 4. Remember, small x is the individual outcome, so they tell you the outcomes. They have to. If they're not going to tell you what the actual experiment is, then they have to tell you the outcomes. And they also say that the probability of x equals x, that's a small x and that's a big X, is equal to k over x squared when x is 1, 2, 3, and 4, and 0 everywhere else. And then what they'll do is they'll pull in a curly bracket like that, and people see that and they start getting afraid. Right? But don't get afraid. What does this mean? You just have to take a step back and understand that this is actually very simple. It's telling you the x values. Great, I've got the outcomes on a plate for me. Brilliant. X is 1, 2, 3, and 4. It means whatever my experiment is, I can only get a 1, 2, 3, and a 4. And what does it say? The probability formula, effectively, the probability for whatever my experiment is, when it's equal to the specific x, 1, 2, 3, 4, 1, 2, 3, 4, it follows the formula k over x squared, where k is just a constant, it's a number, I just don't know what the number is right now. Now what does this mean? 0, otherwise, it's just enforcing the idea that my outcomes are 1, 2, 3, and 4. If I don't have a 1, 2, 3, 4 outcome, I don't have anything. Remember, if the probability is 0, it means it's not happening. Cannot occur. So the only outcomes are 1, 2, 3, and 4. When you've got an outcome of 1, 2, 3, and 4, it follows that formula. And if you don't have an outcome of 1, 2, 3, and 4, the probability is 0. So there are no other outcomes. Now you might say, well, why do I need to write this whole 0 otherwise? It's just complicating things. Because there are certain distributions that follow different formulae for different outcomes. So you could have an example where the probability x equals x is, say, k over x squared for outcomes 1 and 2. It could be a difference of q over x for 3 and 4, and so on. And when you put 0 otherwise at the end, right, that is our way of saying, okay, that's just confirming those are the only outcomes, that's the formula it takes for those outcomes, and there are no other outcomes. That's it. So let's just get rid of this, because that was just my explanation. If I want to create the probability distribution, I just have to use this information and present it in a more meaningful form. So we're told the outcomes over here. So let's do our small x letter for outcomes 1, 2, 3, and 4. Let's create a label for the probability row. And let's do exactly what it tells us. If I want the probability when the experiment is equal to 1, when I get 1 in my experiment, well, if you put 1 in, you have k over, remember k is a constant, okay? But look, it's a formula in terms of the outcome. So if I want the probability when x is 1, then I put 1 in here. So it's k over 1 squared. Just k over 1, which I'll simplify to k in a minute. When the outcome is 2, the associated probability is k over that value, that outcome, squared. So it's k over 4. When x is 3, it's k over 9. And similarly k over 16. And you might think, great, that's my probability distribution. Not so fast. In statistics, we are much more interested in the actual numbers. Yes, we use algebra a little bit along the way. But really, I want my probability distribution with numerical outcomes for my probability. Very rarely do we consider algebraic probabilities. When we look at a probability, I want to know the number. I want to know what it is. A half, a third, a tenth, whatever. So, can I find k? I've used that information. What's there more to do? So you have to pull out the bag an obvious fact that is overlooked, which we mentioned already. The fact is, these are all the outcomes, these are all the probabilities. Now, what do I know about all those probabilities? All of the probabilities add up to 1. These are all the outcomes, so if I sum up all the probabilities that we saw before, they add up to 1. So I'm going to apply the principle that the sum of all of the probabilities, okay, must add up to 1. So I end up with k plus k over 4 plus k over 9 plus k over 16 must equal to 1. And you have to solve k out of that. And I wouldn't recommend sort of trying to get sort of common denominators. You can, it's just a bit messy. I simply would just take k out as a factor, because it appears in every term. 1 plus a quarter plus a ninth plus a 16th is 1. That's 205 out of 144k, which is equal to 1. And if you sort that out, then I'll put it up here, then k is 144 out of 205. And once you have k, you can then put it in. So then you can rewrite the table. So you have 144 over 205 over there, you put k in there, divided by 4, put the actual number there, there, and then you can check that those numbers indeed add up to 1. And if we do that, that was k over 1, so that's 144 over 205. If you divide that by 4, that will go down to 36. This will be 16. And this will be 9. We've got messy fractions there, but that is commonplace in the A levels, so don't be put off by that. And just remember, when we're doing a probability distribution, we need to have the probabilities as numbers. If you get algebra, there's always a way to get the value of k. It's usually by summing up the probabilities and forcing them to be equal to 1. So, apart from the probability distribution and formulating that, what could they ask you? So, let me give you some questions, and I want you to think by yourself how you'd solve them. So what I'd like you to work out, I want you to work out some probabilities. Right, P x bigger than 2. Part B, I want you to work out probability 1 less than or equal to x, strictly less than 2. Part C, I would like you to work out the probability that that x is bigger than 5. Now those three are quite straightforward. The fourth one is going to require some thought. It's going to be a little bit tricky. So part D, I'll write it up here. Try this. Part D, what's the probability of x squared being less than or equal to 1? That's one to think about. So have a go at those 4 questions. Have a go, press pause, and then you press play, and I will go through them. Okay, so part A, probability that the random variable x takes a value larger than 2. So let's look at the table. This is why I said you need the probability distribution to answer whatever they want to ask you. So what's the probability that the variable takes a value bigger than 2? Well, what values are bigger than 2? 3 and 4. But what's the probabilities of those? So you need to pick up the 16 out of 205 and the 9 out of 205, which is 25 out of 205. Of course, those numbers both end in a 5, so that will cancel down to 5. Sorry, it's a bit small. 5 over 41. Right, part B. Part B says, what's the probability that the random variable takes a value between 1 and 2, including the 1, but not including the 2? It's a strict. You have to be careful with these inequalities, are they strict or not? So between 1 and 2, including the 1 and not including the 2, well, between 1 and 2, I'm not allowed to have the 2, and there's nothing else between 1 and 2. So it's just this. It's exactly that. That's actually the same as probability x is equal to 1. So that is simply that probability over there. So part B is 144 over 205. Part C. What's the probability that x is larger than 5? Well, the random variable, this experiment, cannot have a value 5, or let alone bigger than 5. It only goes up to 4. So it's not a trick question. That cannot happen. Even if x is strictly bigger than 4, that can't happen either. Therefore, if that's impossible, and we know impossible events are represented by a 0 probability. Now, for part D, which says probability x squared is less than or equal to 1, let's make some space up here and do it here. Right, now, the issue with part D, which asks as follows, probability that x squared is less than or equal to 1, the issue is, how do we understand that? Right? I understand what this means. This means, what's the probability that whatever experiment you're doing produces values bigger than 2, outcomes that are bigger than 2. I understand that. What does this mean? What's the probability that when I do my experiment and I square it, that result is less than or equal to 1? It's just too much to think about. Okay, I'd have to worry about squaring the outcomes and then seeing which are smaller than or equal to 1, which you could do. Okay, you could do it like that. It's simpler to change the probability statement. Probability of x squared is less than or equal to 1. Okay. What we could do is say, well, actually, let's take that out. Let's take that out for now. Okay. If x squared is less than 1, what do I usually do with that? Well, it's a quadratic inequality. We can solve that. So we can do x squared minus 1 is less than or equal to 0. Solve it in the usual way. X plus 1, x minus 1. We've got critical values, roots of 1 and minus 1. So the graph would look like this. And we want the bit that is less than and including 0, which is everything in between minus 1 and 1. So that can be written as minus 1 is less than x is less than 1. That inequality can be solved and rewritten as this. Okay, they've only given it to you like this and like that, just to make it look a little bit more complicated than it really needs to be. Now, let's answer the question now. What's the probability that my random variable takes a value between minus 1 and 1? Well, my random variable doesn't have outcomes. There's nothing before 1. Right? So from minus 1 all the way to 1, okay, there's nothing from minus 1 to 1. There's nothing in that range until I get to 1 itself. So between minus 1 and 1, the only values there that exist and have probabilities is the actual 1 itself. We're lucky that that's included. Otherwise I wouldn't get anything at all. So actually from minus 1 to 1, the only values that exist in that range is 1, which has a probability of 144 over 205. That's it. So therefore the answer to this is the same answer I got for part B. 144 out of 205. Alternatively, the understanding of that statement means if you were to square the outcomes from this experiment, how many of them are less than 1? So if you have 1, 2, 3, 4, if you square each of those, you get 1, 4, 9, and 16. Those red values correspond to x squared, the square of the random variable. The only value there that has a squared value less than or equal to 1 is this one over here. And then you pick up that probability. But when you start squaring and it's a bit confusing, you've essentially got two random variables at the same time. I think going down that route is a little bit complicated and I'd avoid it, especially if this would even be more complicated. The idea is when you've got something more complicated in your probability, try and solve it and then bring it back together like we did here and you get 144 over 205 for that example.